So now we're going on to the next part of stellar evolution, where we talk about what happens after the red giant branch. So here's what we were looking at in the last segment, where the star has become a red giant star and the helium flash happens, and so helium burning has begun. During the red giant phase, you have non-burning helium in the core, and you have helium fusion in a shell, and then you have most of the star not doing anything. In this phase, we're going to go through a second red giant branch, which is called the asymptotic giant branch, because it asymptotically approaches the red giant branch. And you can see here how it has slightly different structure. So now we have carbon in the core, we have a helium burning shell around the core and a hydrogen burning shell around that, and still lots of star that is not burning. And I want to emphasize that these cartoons are not to scale. The region where burning is happening is much smaller than the rest of the star. So just to clarify, we've gone from main sequence where we have core hydrogen burning to the red giant phase where there's nothing burning in the core, and you have hydrogen burning in a shell, to what happens after that. Once helium can burn, you've got a helium core burning region, which is the horizontal branch, and hydrogen burning in a shell, and then nothing happening in the outer regions. So what's actually happening? Oh, I want to just point this out. So this is a figure I got from a textbook. When the star gets to here, that is the top of the asymptotic giant branch. It is an AGB star, named for the asymptotic giant branch. It is not a planetary nebula until it gets over here, which we'll come to. But the textbook had it as a planetary nebula right here. And so this is something that we should be concerned about, is textbooks aren't always correct. Okay, so just to emphasize what's actually going on. So we've had, the core has started burning helium, and just like we had with the hydrogen, eventually you're going to run out of helium. It's a finite resource. And so you're converting helium to carbon through the triple alpha process, and eventually there's none left, it's all carbon, and so we go back to the core is collapsing because it's not producing anything, and so it cannot balance gravity, and so it's collapsing under gravity. And so the core is shrinking and heating up just like we had before. Now, though, we had a hydrogen burning shell around the core before, and that's now full of helium because it's converted the hydrogen into helium, which is also shrinking. So we have a shell of helium around the core, which is also heating up, and that will switch on, just like we had the hydrogen burning shell during the red giant phase. And there's a hydrogen burning shell, and this is how we get the structure. So we have a carbon core that's not burning, we have a shell of helium that is burning, and we have a shell of hydrogen which is burning. Now actually these are not on constantly, and they may switch on and off, which I'll come back to. But just like we had in the red giant phase, we now have these two switching on and inputting energy into the remaining inert shell, and so that is going to heat up and expand, and so we get a red giant again. Only because we have two lots of burning, we have the red giant branch and the we have the hydrogen burning and the helium burning shells, we have more energy, so it's brighter. So it's up here, and it's actually almost as bright as supergiants. But in this case, we never get to the point of burning carbon, and I'll come back to that in a second. Now, the helium behaves in a similar way to it did in the core, but now it does some other things as well. So what we get is that the helium burning actually switches on and off. Basically, you switch on the helium burning, it's shrunk, it's gained energy, it switches on. Sometimes it will become degenerate before it switches on. Remember, we also have hydrogen burning, which can put energy into the shell. And then when it switches on, you get this flash through there, and it increases in brightness. But then it will also increase in temperature, overcome degeneracy, and expand. So the shell expands. If it expands, it's using energy, and it cools. And it cools below the point at which helium fusion can happen. So it switches off again. When it switches off, it's no longer making energy, so it's going to collapse again, so it contracts and heats up. And then you get ignition again, and so on, and so on. And so what you get is what's called thermal pulses. And here you can see how this manifests itself in the brightness. So you've got the helium burning is not on, the helium burning switches on, and then the shell expands and cools, and it switches off again, and then it switches on, and then it switches off again, and then it switches on. And this is showing you the time scale for this. So it's of the order of 100,000 years between switching on and off again. And this is for a solar mass star. So one solar mass star would go through something like this. And this is really important for the details of what happens inside these stars. but it also means that your star is changing size and brightness. You can see here, this one's going from less than 2,000 solar luminosities up to nearly 10 to the 4. And so it makes a big difference to the brightness. Now, as I said, the core is now carbon, but it doesn't collapse anymore. It's just like we had with the helium core, it becomes degenerate. And so it can't collapse anymore. The electrons are as close together as they can get. The problem is that even with the helium burning and the hydrogen burning, the amount of energy that's required to get the core up to the temperature to fuse carbon is just too high. We can't get there. And so this is as far as this star goes. And this is true for stars up to about 8 solar masses. So if they're below about 0.8 solar masses, they don't even get past helium. It stays degenerate. It never goes past that, which I'll come back to. If it's between about 0.8 and 8 solar masses, then it will manage to fuse helium to carbon, but then it won't go any further. As you've got more massive stars, you can go on to the next step and you can fuse carbon and so on. And we'll get onto that when we talk about high mass stars. Okay, so what happens next? Well, all stars lose mass. We've talked about this. The sun has a solar wind, and they're also using mass to turn it into energy. But for these stars that are more massive than the sun, they also have stronger solar winds. But once they get to this phase, when they're in the asymptotic giant branch phase, they lose mass even more strongly. And this is caused by various different things, but basically it's losing mass at about 10 to 100 million times the mass loss of the sun. So it's losing, of the order of a millionth of a solar mass per year, which doesn't sound like a lot, but the sun loses it at 100 million times less. There's a lot less material lost by the sun. But at the same time, the expansion velocity is not very great. It's only moving at about 10 to 20 kilometers per second, as opposed to the 100 or 1,000 kilometers per second that the solar wind has. So you have lots of mass not moving very fast, so the density of gas around the star that's drifting away is very high. And so what we see here, this is the Egg Nebula. There's actually a star behind this dark part, and then here you can see this is dust that is formed, and it's basically you've got gas flowing away from the star, and just like you'll get soot forming above a fire as the gas that's off the fire cools, you will get dust that is possibly like soot, more likely like sand, and it will form, and then you have cosmic dust. And this is actually where my research area is, so you can feel free to ask me lots of questions about this. So what happens next? Well, at this point, you've got a star, it's lost a lot of material. A star like the sun will lose about 40% of its mass. At the top end, around 8 solar masses, it could lose 80% of its mass through this mass loss process from the dust. And it will, what's left, eventually you've lost enough mass that there isn't enough material left in the star, and what's left just doesn't have the pressure to support itself, so it will start to collapse. And what happens is that it collapses in such a way that although it's getting hotter and smaller, so it stays at constant luminosity. Remember that if it heats up, it should get brighter, but if it gets smaller, it gets fainter. And so what you get is those two trading off against each other, so it stays at constant luminosity. And eventually the collapse means that you have, at the surface, you've got this gas that's above 30,000 Kelvin. So it goes from 3,000 Kelvin, and in the course of a few thousand years, it actually gets up to over 100,000 Kelvin. Once it gets to 30,000, that's where you can ionize the hydrogen. And at that point, we have what's called a planetary nebula, which I'll get into in a second. I want to emphasize that the term planetary nebula is historical. Basically, when we had small telescopes, when these things were first discovered a couple of hundred years ago, they were aware that they were clouds of gas, so they're nebulae, but that they looked like planets do. Now that we have great high-resolution images, they don't look anything like planets, but at the time they looked kind of like round things that weren't stars. And so the idea of planetary nebulae was a nebula, a cloud of gas, that looks like a planet. So don't confuse them. Like I say, you get this continuation that the star continues to contract and heat up, and eventually it runs out of space. It can't contract anymore, and it gets to that point. But at the same time, you've got all this material that was drifting off. It's made dust. It's a shell of material that's just moving out according to Newton's laws. There's not much. The gravity is not pulling it back. It's achieved escape velocity. It's drifting off, and so it's moving out. And so that is what is illuminated by this really hot central star. And so it basically glows like a neon light. Now, before we can understand what we see, we have to talk a little bit about how we're looking at stuff, because these things are dusty. And so if we're at this point, and the star is over here, then we may or may not be able to see the star. It depends on the dust. You can think of this as being a bit like fog. Depending on the size of the particles and the compactness, the density distribution of the particles, you will actually maybe be able to see through it, but it'll be kind of foggy, so you'll lose some light, or you may not be able to see through it at all at visible wavelengths. Remember, this depends on the wavelength of light that you're looking at. On the other hand, you can get some reflection off here. So if the star is here and there's a dust cloud here, you'll get reflection. And so you can use both of these to determine what the material is around your star. And so this is just another way of looking at that. And so basically you've got dust here, you've got starlight hitting the dust. Some of it will go straight through. Some of it, the redder it is, the less it will be scattered. And so you get red light going straight through and blue light being reflected. This is Rayleigh scattering. This is actually why the sky is blue. At the same time, so we get to see this, but if you're over here, you can get to see reddened light. If it's really dense, you won't even see red light, you'll see infrared. But you'll also have stars inside a cloud which are ionizing the gas, so you'll get glow from the gas, which is like the neon light. But there may also be dust that's interfering with that. And so what you see really depends on the geometry of the system and the heating of the cloud and the temperature of the star inside it. So here we come back to this, the Egg Nebula. What's going on here is this star is only about 7,000 Kelvin. It's not able to do any ionization yet. And so what we've got is there's actually a star hiding inside of this. So this is actually like this. You have a torus or a donut of thick dust. The dust is so thick that it blocks the light. If you look at this in the infrared, it's actually glowing quite brightly because the dust glows in the infrared. There's a star in here, but because it's like this, the light can escape top and bottom, and then it's being reflected off of these spherical shells of dust that have been ejected during the RGB phase. This is a star that's a little further along. There's actually a star further in here. This is a planetary nebula, a very young one. This is also reflection from dust here. And you can see here that it was spherical and then it became very, very bipolar. And actually we don't fully understand why that is. And you should feel free to ask me questions about that. And this is another example of a bipolar planetary nebula where the glow that you're seeing here is from the hydrogen that's being ionized by the star that's in the middle. And so here I just have a nice little slideshow of I have some information first. So this is the Helix Nebula. This is one of the best studied. You can see it in August very low in the southern sky. It's basically a southern hemisphere object, except that you can't see it naked eye. You need a good telescope to see it. But to give you some perspective, this disk is about the size of the moon, the full moon of the sun, and so it's actually very large. And one of the problems is most of our modern telescopes can't capture all of it at once. But this is the Helix Nebula. It's very close by. It's about 200 parsecs away, and so it's very well studied. But all planetary nebulae are basically remnants of stars that they have about one solar mass left in the middle. It depends on what the star was to start with. The whole size of this is going to be, several light years across. It could be tenths to a few light years across. It's expanding. We have data on this, so it's expanding of the order of 10 to 20 kilometers per second, and they're generally less than 10,000 years old. How do I know this? Well, I know the distance from the central star to where the material is, and so I can calculate, and I know how fast it's moving, so I can calculate how long it's been going. And so many of them are much smaller than this. This is quite an old one. This is actually almost 20,000 years old. And just to reiterate, nothing to do with planets. And so this is my slideshow. So this is actually the Dumbbell Nebula. This is an image that was taken from the ground in near Tucson at Kit Peak. And it is taken actually two images pasted together. So you get the pink. So the pink is hydrogen, and then the yellow is ionized oxygen. And the dumbbell was the very first nebula ever to be discovered, planetary nebula. This is actually an infrared image of one of the ones we already looked at, this is called NGC 7027. That's what it looks like in the visible light. This one is the hourglass, made famous by Pearl Jam. This one doesn't have a name, it has an NGC number. This one is called the Eskimo. Apparently this looks like the rim of a parka, and this is the face. This is the butterfly nebula. Lots of them claim to be called the butterfly. This is the butterfly. This is the cat's eye. This is NGC 6543. This is the ring nebula. This was the second nebula to be found shortly after the dumbbell. And this is the helix again, only this is a much better image. This is a Hubble Space Telescope image than that first one we saw. And here the colors are, this is ionized helium, and here you've got a mixture of green and red, where the red is actually ionized nitrogen, and the yellow is where you have both the nitrogen and ionized oxygen. Okay, so how do these things actually form? Well, it's basically a two-stage process. So we have the mass loss during the AGB phase. So we've got an AGB star. It's losing material, mostly in all directions, although it's not clear when it stops being in all directions. So you've got this material. And then once you stop losing mass, you're shrinking down the star, but it develops a fast wind, which is more like the solar wind. So it's not losing much mass, but it's moving much faster, and that compresses and causes shocks in this inner region. There's also the fact that the mass loss rate increases over time during the AGB phase, so it's already denser here than it was early in the mass loss phase. And so what you get is a compression of the material, and then the star gets hot enough to excite this material, and it glows like a neon light. And so now what we've got is something that's basically in two parts. You've got a star in the middle, and then you've got this gas around the edge. The size of this thing is at least the size of the solar system. In fact, for the helix, it is much bigger than the solar system. In fact, you've got these little tiny clumps here. In the helix, these clumps are about the size of the solar system out to Pluto. You can see here we've got several different shapes. You also saw different shapes. And like I said, it's not clear whether some of this is orientation, so we may be looking down the barrel here, or looking side on here. It's clear that that doesn't explain all of the shapes, and we don't really understand how they get there. But the center of this thing is basically dead. It's not a star anymore. It's a white dwarf. And the nebula will continue to expand so that it gets to low enough density that we can no longer see it. And so some stars may not ever have a planetary nebula, just because if they expand too fast and there isn't enough density, we won't see the glowing gas before it's dissipated. And just as a reminder, the central star is now what we call a white dwarf. Technically, a white dwarf is not a star because it's not doing fusion. And the nebula is the last densest part of the star's envelope that was ejected. So basically, the very last bit of the thing loses mass over 100,000, a million years, depending on the mass of the star, and it's increasing all the time, and so it's the densest part that we actually see. And it glows because the gas is ionized. And so that's what we're seeing in these nebulae. So this is just showing you some of these again. And you can see that they're generally either kind of circular looking, like this, or this, or this, or they're kind of bipolar looking. And so what we've got to so far is we've gone from the main sequence to the red giant phase. We go through the yellow giant is the core helium burning phase. And then we've got the red, here it calls it a supergiant. Technically it's an AGB star, but it's bright enough that it's right at the transition between giant and supergiant. And then we get a planetary nebula, which dissipates, and we're left with a white dwarf. And you can see here that this is based on a one solar mass star, so it spends most of its time as a main sequence star, a little while as a red giant, a little while as a yellow giant, even less time as an AGB star, even less time as a planetary nebula, and then the white dwarf phase. It takes a long time. It's not actually white the whole time, but it takes a long time to cool. And so for the sun, this is showing you what happens. So you've got the time here to the next stage. This is the main sequence. This is the red giant phase. This is going up the red giant branch. This is the core helium burning. This is the asymptotic giant branch. and then here's the planetary nebula phase. And you can see the sizes of these things. So in the red giant phase, it's about 100 solar radii, which, to put that in perspective, we can put that in AU. It's about half an AU. So it doesn't actually engulf the Earth yet. On the other hand, when it becomes an asymptotic giant branch stars, it can be up to 500 times the radius of the Sun now, which means that the surface is out by the asteroid belt. It engulfs Mars. And so it's huge, and all the other planets are destroyed. And so I just wanted to give you this sequence. So we go from main sequence to red giants. The helium flash depends on the mass of the star. So if you have a low mass star, it never even does a helium flash. And you can have a planetary nebula, but you don't usually expect to. But you'll have a white dwarf that's just made of helium, because the helium burning never switches on. If you've got something that's at the low end of the intermediate masses, so around 1 solar mass, goes through the red giant phase, but then you get the helium flash, and then an AGB star, planetary nebula, and a carbon-oxygen white dwarf. This is just what's left over. This is the core of the star that's left over. We have the main sequence for slightly more massive, say above about 4 solar masses, still the red giant phase, but now you don't get the helium flash because it's hot in the core, and we'll get on to why that matters. And so it goes through, and it does burn helium, but it doesn't flash, it doesn't become degenerate. And so we get an AGB star, and a planetary nebula, and a white dwarf. And so we've got stars that are very low in mass. We get stars that are intermediate in mass. We get white dwarfs, and the white dwarfs range in mass. So the star has to lose quite a lot of mass. If it's a 1 solar mass star, it becomes about a 0.6 solar mass white dwarf. So it loses 0.4 solar masses. But you have to go down to about 1 solar mass if you are an 8 solar mass star. So you have to lose a lot of material. And that phase lasts of the order of 1 million years. And all of that material ends up in that circumstellar shell. It's drifting off into space. It forms dust and molecules, and it becomes the next generation of stars. And we'll come back to that idea later. So here I've got my planetary nebula. I've got all of this dust and gas. It's drifting off into space. Eventually we'll join stuff that came from other stars, so we get a dark cloud. And this is a dark cloud where there's dust and molecules. It's blocking the starlight from behind. This thing might get hit by a supernova shock or something like that. It starts to collapse, and then we get star formation. And each one of these tiny little knots is a star trying to form in a big cloud. And then you end up with a forming star with a disk that may form planets. Here you can see an artist's impression of that disk. Until eventually we have a star again. This one should look familiar, I hope. And then that will evolve and end up as a planetary nebula, and so on. So we have this life cycle of stellar material, and during this phase it will make new material, new atoms that will be ejected into space. And so just to kind of summarize this evolution before we get onto white dwarfs in detail, I've got a solar mass star on the main sequence. It becomes a red giant. It goes into core helium burning. It becomes an asymptotic giant branch star. The circumstellar shell expands while the core of the star contracts, gets hot. We get a planetary nebula. All the while the shell of material is drifting off until eventually we just have a white dwarf. And the white dwarf has no way to make energy. It is degenerate. It's made of carbon and oxygen, and so it just cools. And it cools according to its temperature and its surface area. And so this is just a summary of that idea. So it just gets dimmer and dimmer until eventually it would be a black dwarf. Actually, the timescale for this is so long that I don't think there are any yet over the course of the age of the universe. And so that is it for AGB stars. We'll come back to this idea later.